Wait, can people hear me at all? Oh yeah, yeah, Michelle said yes. Okay, okay, yeah. Good stuff. Okay, Jesse, what's your question? Wait, Jesse, I thought your hand was up. Oh, you didn't have a question. Okay, good, good. Okay, so I hope everyone is doing well. I hope everyone is fine. We have a lot of things to cover today. So last week, we covered various graph problems. We went through topological sorting, where we simply said topological sort is something like we give you a bunch of items and a relationship between them, and we ask you what will be the right way to to arrange these items in a specific order. So for instance, we use the courses one, right? Like if I have a course which has a prerequisite, right? So take course 5, you have to take course 2, to take course 2, you have to take course 1, to take course 1, you have to take course 6 and course 4, right? And then to take course 7 or take course 6, and we ask you what is the order in which you can take these courses, right? And that order is called topological sorting, right? So we went through an algorithm to basically kind of return the output, right? We went through the base cases like this, went through the recursive case, went through a way in which you can accumulate the results, right? So for instance, if the course has no prerequisite, you can complete it early, you can complete it first or something. And if you complete, the courses too, then you can also add it to your result variable. This is very good stuff. If you weren't here last week, please, I advise you watch the recording. Now we put the recordings on YouTube because our Google Drive space is getting limited over time. Then secondly, we want to know this cool question. We wanted to think about, solving graph problems, in a reverse manner, right? That instead of starting from inside and going out, sometimes for graph problems, it helps to start from outside and come in. So we look at this problem, which was, kind of like the crux of the day. That was a bit challenging, where we are like, okay, assume, this is a Pacific water flow, and even if you don't just think of this whole thing as the ocean, right? Think of this whole thing as the ocean. Then we're like, we want to select those cells from which we can get to the ocean from, right? So we have this whole ocean here. We want to go from, any of these cells to the ocean. But we said that you can move from one cell to another cell to the ocean if and only if. So if I take this cell 5, right, I can only go to cell 4 and then cell 0 and then to the ocean because 5 is bigger than 4. When I get to 4 is bigger than 0, right? So you can only go from one cell to another cell if you are bigger than than that next cell, right? So that is what we discussed. So and we said, so if you take 7 here, right, we cannot go from 7 to 8 to 9 to the ocean, right, to this blue ocean. That is impossible. Why? Because from at 7, right, this is a wall, right? 8 is taller than 7. I cannot jump down this wall, right? Because 8 is bigger, right? And even if I get to 8, I cannot do the same thing. Right? I cannot jump from 8 to 9 because 9 is, a wall is bigger, right? So I can't do that, right? And we said, one algorithm is to simply, iterate through every, possible cell. When you add some cell, then you try to, jump out, you try to flow out, right? But we said this is, inefficient, and this also wastes a lot of time. Instead, you think of it this way. Instead, you try to start from the ocean, right? Start from the ocean, then you try to see which points, right, which cells you can get to from the ocean, right? If I start from the ocean, I'm like, this is 2. I'm like, okay, so I can get to 2. Obviously, can get to all the border cells, right? That is very obvious, right? Because for every border cell, you can just jump to the ocean straight. If I start from 2, right, then I will ask myself, considering each neighbor of 2, right? So if I consider this neighbor that is 4, is it bigger than 2? So we see now the relationship reverses, right? So I'm like, from 2, is this neighbor bigger than or equal to 2? If it's bigger than or equal to 2, I'll call my function recursively on 4, right? So now I accumulate 4, 2. That means that I could get to 4 from the ocean. That means I can get to the ocean from 4, right? Kind of like a reverse thinking, right? So the old solution is to start from 4 and see if you can get to the ocean, right? But we're like, no, now try coming from the ocean, right? Start from the ocean, you can get to 2, right? Then from 2, try to see if you can recurse on this neighbor 4. And what's the condition to recurse? Is 4 bigger than 2 or is 2 less than 4, right? It's the same thing, the same algorithm. Then that's the case recurse. So that means that you accumulate 2, you accumulate 4. Then 4 to get to the neighbor 5, you ask the same question, right? Is the neighbor, bigger than or equal to 4, or is 4 less than or equal to the neighbor? If that's the case, accumulate it and recurse, right? Then let's say you get to let's say this, you get to something else. You get to this guy here, this 4 here, right? Here you don't recurse here, right? Like you don't recurse on this guy. Why? Because this guy is bigger than this guy, right? So that's basically one way of going through this question. And I showed you a problem you can actually solve to get more hands-on practice. And I hope people really did it. Today I'm going to do another question. So I'll grade this question as I'd say level. I'll put this question as let's say level 3, right, of graph problems. But let's look at the level 2 version, right, which I think is going to make things so clear to people, right? So I believe people have understood, this pattern of questions where you get the input and you construct your own graph dictionary from it. But I want to just look at another question that involves matrices like this, right? I want to look at a question like that. That is really going to help, right? So let's look at the question we have here. Please follow me carefully. Even if this water flow thing didn't make sense to you, follow me on the next one. It's really going to make a lot of sense to you. I just want to show you how you can, manipulate, matrices that represents graphs. Okay, so let's assume we have another grid like this. And now our grid is less interesting. What do you mean by less interesting? Our grid actually is a bunch of zeros, right, and ones. Okay, so our grid is a bunch of zeros and ones. And the question is, we want to count the number of groups of ones. The number of groups of ones. So this is what the question is asking us to do. That I want you to go through this and count for me the number of groups of ones. So this is what they mean. So a group of one is connected. So then you ask the interviewer, they explain to you, a group of ones is connected either in the north, south, east, or west directions, right? So for instance, this is this whole thing, right, is a group of ones. So this, let's just do it here. Is it like a highlighter? Okay, this whole thing, right? This whole thing you see here is a group of ones, right? Can we all see this whole thing here is a group of ones? Can anyone see? This whole thing is a group of ones. Why?
Wait, Cornelius?
Yeah.
Can you take your time? I think some people can't hear you. Give me a quick second.
Oh,
Um,
who can't hear me?
I think Jesse can't hear you.
Oh,
I don't know why. Can everyone else hear Cornelius? Just to make sure it's not from him.
Yeah, I can hear it perfectly.
Yes,
just probably check your. Have you connected your audio to Zoom? Have you joined Zoom with your audio? Maybe you haven't. Let me see if you have. Let's see. I don't know. Maybe just try joining again, and then when they ask you to join audio, yeah, I think it's probably an audio thing.
Yeah, like update your Zoom or something because it seems it's from your end.
Yeah, and let me know what happens. Okay.
Sure, continue.
Yeah. So the question is, want to count the group of ones, right? So if you look at this grid here, this is one group of ones. Why? Because all the yellow ones I've highlighted are connected either in the north, south, east, and west way. So if I start from this one, right, it's connected to this one. This guy too is connected to this one, right? Like, does everyone understand it? This is also another group of ones. So here we have two groups of ones. Does this make sense? Does this make sense? Right, this is basically what we are looking for. We just want to find how many groups of ones there are. So in this question, there are two groups of ones. I could also, change it and maybe make, some one here, right? If I did put some one here, then we have three groups of ones, right? This is also another group of one. And the question is, how do we do this, right? So this is a graph question, as you can see. How do I know it's a graph question? There's a concept of a neighbor, right? If I take this guy here, right, this one is his neighbor. And if I take this guy here too, this guy is his neighbor, right? Then this guy too, this one is his neighbor, right? So it's a neighbor, thing, and graphs show these neighboring relationships, right? So this is purely a graph question. That's why we can know a graph question. If I take this guy too, this one is his neighbor, right? If I take this guy too, it's his own neighbor, right? And then I get this, and I get my answer perfectly. So we're going to write the solution. I'm going to code out this thing. It's going to like really help. It's going to lay, the foundation for, many graph questions with grade. So how you do this question usually is now, please follow me carefully. Follow me carefully. So we just want to count the number of ones, right? So let's write that function. Def count, let's just def count ones, right? Count ones groups, right? Then here I'm going to give you, the matrix. So one thing you do is, all we're going to get the matrix, take the dimensions of the matrix, right? So let's take the dimensions of our matrix. So we're going to take the dimensions of the rows, how many rows there are. That is simply the length of your matrix. And then you count how many columns there are also. So columns is simply going to be the length of your matrix index 0. So if you've forgotten this, we did it about 4 weeks ago when we were doing dynamic programming and matrices. So we said, so the rows are simply these things, right? These things, right? The horizontal ones, right? So that's what we mean by length of matrix, right? Then a column, right, is if you take, matrix index 0, right? If you take like this first, this first row, right? This first one, count how many elements there are. 1, 2, 3, 4. That is basically a number of columns, right? So that's how you get the number of columns. The next thing you do is, now we don't know, now listen carefully, we don't know where, where the first one is going to start from. So all we can do is to simply start from, any cell, right? From every cell. So we're simply going to be like for every, right? Let me choose a different color for that. So we're going to be like for every, for row in range rows, right? Then we're also going to be like for column. So we already discussed how to loop through a matrix for column in range columns. Now the question becomes, when do we trigger some function? Now, assume there's a certain function that is able to, find all your neighbors for you. If I start at you, just assume that there's a certain function that if I call a function on 1, this function is able to, spread its wings and go and find for me all the ones that form a group, with this 1, right? So let's assume there's such a function. So the question is, when do I call such a function? Should I call it on 0? Should I call it on 1? Or should I call it on both of them, right? And that is where the optimization comes in. Right, so anyone, so can someone answer, when should I call this function? Let's assume that function is called DFS, right? Let's assume there's a certain function here called DFS. And what DFS does is that it's going to spread its wings, right? And find for you, all the ones that form a group with you. So when should we trigger DFS? We are still here inside the count ones group. When should we call DFS? Anyone? On what cell should we call DFS? On what cell should we call DFS? Yes, anyone. Let's feel free. Let's feel free. On what cell can we call DFS? Let's not overthink it. So we said DFS counts the number of ones, right? It expresses its wings and finds for you. Good, exactly. So we only trigger DFS, right? It's an optimization thing. You trigger DFS if, right? So if the current cell is a 1, right? If matrix of R and C is a 1, right? Then, so let's use a different color. I like to split the parts so people can easily see when they're reviewing. Okay, so let me just change the color. So if, right, if matrix, right, of row column, that is if the current cell is a 1, right, if it's a 1, then I'll call my function, let's call it spread wings. Let's call it spread. I think that's a more relatable name. So then I'll call spread, right, I'll call spread on. Spread going to take the current row and the current, what do you call the current column. So this is what we have here. So spread, row, and column, right? And what am I believing? I'm believing that when I call spread, right? When I call spread, it's going to spread its wings, starting from the current row and column, starting from the current cell, and find for me all the groups of 1. Does this make sense? Does this make sense? Does this make sense to everyone? We're almost there. We are almost there. Okay. Okay, good stuff. Now let's proceed. So then that is basically going to my whole thing, right? Then next thing, don't even think about the implementation of spread right now. Don't think about it, right? But then the question is, let's think about something carefully here. Now, if I got to this one, assume that the first time I call spread, let's say it was this guy, then it spread, then it went to count, the number of, ones, it went to count the group that's, that this guy is a part of, right? So spread has returned, right? So we have got 1 here. Then, I called spread on this guy. When I called spread on this guy, then this guy, spread went through and spread found everything, right? Spread found this long yellow chain for us, right? Then spread returned. The question is, when I get to this 1 again, should I call spread, right? Should I call spread? Anyone? Should I call spread? So when I got here, I called spread, right? And spread already found it for me. Spread, when I got here, I called spread and spread found this long yellow chain for me. When I get to this other one, that is a part of the same old chain. Should I call spread? No, I shouldn't call spread, right? I mean, you can call spread and optimize it, but ideally you don't call spread. So let's see what we're going to do here. We're going to revise the definition of spread. And I'm going to be like spread, right? Spread simply, I finds the group, right? Finds the group from which the chain starts at. So what I'm simply saying is that if I've already identified a certain chain and I find a certain node, right, of which, which is part of an already found chain, I'm not going to trigger spread. So the question now is, how do we do this, right? Now listen carefully. Don't think about code, think about the algorithm right now. How do we do this? So this is how we are going to do this. Now, if I got here, right, and I call spread on this, what I'm going to do is that after spread has returned or inside spread, I'm going to flip this guy's 1 to 0, right? Because you know that if the matrix of R of C, right, if the cell is 0, I'm not going to call spread again, right? So if I've called spread on you and spread has already, identified you or walked through you, before I return, I'm going to flip you to 0. Does this make sense? Does this make sense? So assuming I called spread when I was here, spread is going to take, all the cells here and flip each of them to 0. It's going to flip each of these guys to 0 after spread has returned, from this function, which means that if I continue my loop and my loop gets here, the loop is now going to see 0 and it's not going to call spread on it. Does this manipulation make sense to everyone? Is manipulation okay? Only one person. Like, this is a very common thing you see in graphs, right? You can also use a vested set, right? But with matrices, you can ignore the concept of a vested set. With matrices, you can just, just do the thing in place. That's what I'm showing you currently. You can still use a vested set. So I got here first, right? Then I called spread on this cell, right? Then we know spread will go and find, all the neighbors here, right? Then, my loop is going to continue. It's going to finish this, then it's coming. But when it comes here, it's not going to see a 1. It's instead going to see a 0. Then, it's not going to trigger spread on this guy again, right? Because it's a 0. But you know that it became a 0 because of the manipulation you did, right? You've already identified it as part of a certain chain, right? So that's what we're going to simply do. And so each time we call spread, can everyone say that each time you call spread, you should increase your number of, groups by 1. So initialize a number of groups to 0. Can everyone see it? That each time spread is triggered, that means you have identified a new group. Take your time and look at this. That each time spread is triggered, that means a new group has been identified. Is it obvious to everyone? Is this obvious? Okay, so that is basically, the algorithm. Then we can return results, right? So that's mainly the whole algorithm for the main function. When we go to the algorithm inside spread, and you see it's not that bad either. So we go through every cell, right? We go through every cell here. And then when we see, if it's the first time we're seeing a 1, right, or we're seeing a certain cell in part of a certain group, we trigger spread, right? And we know inside spread, every member of the group is going to be flipped to 0. That's the only thing we know about spread right now, right? Then we know each time we trigger spread, then that means we have found a new group. Then we can increase our results by 1. Please make sure this thing makes sense to you before we go to the implementation of spread. Okay, can we go on to the implementation? And please, if it gets to a point where you're like, what did we do here? Please go ahead. And I'm using the colors, so just mention the color. Can be like, what is green? What is blue? I don't even know the colors names. And then we can go on. Good. Now let's go to spread. Very interesting, implementation for spread. So let's see what spread is going to do. So we know spread is going to accept the row and the column. And now we know that row and the column is simply a cell from which a certain group starts at, right? So if I call spread here, right? If inside spread, the argument is, RC, and let's say it was this guy, we're simply going to find the chain, that starts as this guy, right? That starts at this guy. So that means it's going to go here and go here and go here and go there, right? Right. So let's see something here. So we already went through something where we said you get the neighbors, right? And so how do we get the neighbors? We can simply create, a list here, right? That is going to be 1, 0. If you don't remember this, please let me know. 0, 1, minus 1, 0. Then 0, minus 1. Does somebody remember this thing I did? Right. This is just going to help us go north, south, east, and west, right? Then I write a for loop here. I'll be like for the direction row, comma, the direction column in directions, right? The neighboring row, and the neighboring column, their values are row plus direction row and column plus direction column. Please, what I just did here is a very simple thing we discussed, right? So we said that, assume that, let's change colors here. So assume the neighboring row is RC, right? Assume the neighboring row is RC. So assume the current row is RC. So assume it is this guy here. And let's just choose a random guy. Assume it's this guy here, right? I want to go north, south, east, and west, right? So if you look carefully, that is the same as R plus 1, then C, R, then C plus 1, then R minus 1, then C, and RC minus 1, right? Like these four things, it's what I'm just creating using a for loop here, right? Like it's these 4 things I'm creating. You can do it, as I said, you can do it like four times. You don't need a loop to do this. You can easily do it 4 times like this. Like you can call You can do it like 1, 2, 3, 4. But I think a loop just makes the code cleaner, right? So that's the same thing we're doing here. So what do we do now? So now we have got the neighboring row and the neighboring column, right? That's what we have here. What's it? Let's select this guy. What is it? Okay, we've got the neighboring row and the neighboring column, right? Then the question we have to ask ourselves is, can we trigger the function, right? Can we trigger the function spread on the neighboring column? But then if you remember here, we only trigger spread on you if you are 1, right? That's when we trigger spread on you if we are 1, if you are 1, right? So what do? We check. So let's see the conditions here. So we check the conditions, right? The conditions. So condition number 1, we have the out of bounds condition. Don't think of that now. So let's just write it here. If not, right? If the neighboring row is not out of bounds. So let's just write if not out of bounds. I know what out of bounds means. If the neighboring row is not out of bounds, right? Or the neighboring row, right? Or the matrix of the neighboring cell, right? Or we can simply say if out of bounds or the neighboring cell, right, is equal to 0, is the same logic. Is equal to 0, we won't call spread, right? We say continue. We won't call spread. Continue. Does this make sense? What we are simply saying is that now, if we get the neighboring cell, right, that neighboring cell, assuming we are on this one, and we get this neighboring cell and it's this 0, we won't call spread on this. Why? We only call spread to find, the group of ones which you are part of. So we don't need to come here. This is a condition is always almost, you see in the graph question, right? These matrices. There are sometimes you have to call the function. Sometimes you don't trigger it. This is a condition in which you don't trigger it, right? So if I'm here, I don't need to trigger the function to this left because there's no way, this can't be part of the group of ones. This is 0. So we just continue, just ignore it, right? We ignore it. But then, the loop will continue again, right? We say continue, so to come and execute the loop again, then to get the next neighbor, right? The next neighboring cell. And let's say that is going to be, this guy, this one here. Then we can call spread on it. Does it make sense? Does this thing make sense? Does this make sense? This is actually DFS, how the DFS is going to work. So it comes in, right? It comes in, we get its neighbors, right? We get its neighbors. And then what it does is that it gets, for each neighbor, it tries to call spread on it, right? So 1 comes here, it gets its neighbor, you're like, you're 0, nope, I don't call spread on you. But then it finds 1, it's like, okay, then to call the function recursively on this one, gets this one's neighbors to calls the function on it, 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 and that's DFS. Does this algorithm so far make sense? Does this make sense? So if it is 0, right, if these conditions pass, then it will call spread, it will call spread on the neighboring row and the neighboring column. Does this make sense so far? Does this make sense so far? Okay, good stuff. Good. Now, we've not talked about flipping the things to 0. We've not talked about flipping the things to 0. So let's say we can flip to 0. So that's also a very simple addition. So we can flip to 0 when, before we call spread, let's flip the current cell to 0, right? So before we call spread here, right? So let's come here. Just look carefully. I'm just doing it in parts. Let's choose black. So here, we will just set the matrix. And if somebody can see, we won't get a cycle. We flip this to 0, and before we call spread here, we flip this to 0. To 0. Now let's see why it's not possible to get a cycle here. Can anyone tell me why? Why it's not possible? Let's minimize it. So this is the whole code we have here. Can anybody tell me why it's not possible to get a cycle here? And we know what a cycle is. So what we mean by a cycle is, assume that you call spread on this one here, right? On this cell here, right? Right. So you came from here, and let's say you got here, right? And then you go here. Then you call spread on this, right? This guy is indeed a neighbor. Like the one top here is indeed a neighbor of this guy, right? But why will, the function not continue from here? Why would the function return straight from here? Why? Like, why would the function not trigger? Does anyone get my question? Like, we start from here, right? Then recursively, we recursed here. Then we recursed here. Why would the function not go back up to this one? Why would the function not go back up? Exactly, because we changed it to 0, right? Because before we got here, we had changed these two ones to 0, right? And we know that when the neighbor is 0, you continue. You don't call spread on it. So you're not going to be stuck in a recursion hell, right? And trust me, this is the algorithm. And once, so that means that when the first time you triggered, spread on the first cell, like on this one, spread will come and identify its neighbors. And see, the function is the code is so simple. It's just the DFS. Get the neighbors. If the neighbor is not out of bounds, like if you're not outside the matrix, or it is 0, right? If it is out of bounds or 0, don't do anything, don't call spread. Else, set the current neighbor to 0 and call spread on him too, right? So by the time this function will fully return, it will have explored, all the ones that are part of the family, right? And then the spread will return back to here, right? Then you increase your results by 1. Then you go through your loop again, right? If it's 0, you skip, right? If it's 0, you skip. But if it's 1, like you identify a 1 here, then you call spread again, and then it returns, and then we are done. So this is the whole code. This is very common of the graph, questions you would see that involve matrices, right? You have a condition here. Here was our condition. Other than the normal condition of out of bounds, the condition is if it is a 0, don't do anything, right? If it's a 0, don't do anything. But if it's a 1, then you can call spread, right? If it's a 1, then you can call spread. Does this make sense to everyone? Yeah, we're going to see a very pretty algorithm that is going to help you. We're going to solve this question in a different way, actually. We're going to solve it in the typical, very cool stuff way called the union find algorithm. But this is, in case you have it as a grade or something, this is simply the algorithm. Does this make sense to everyone? Before we move on to the next thing, please take a few seconds, look at this, and then we proceed. Somebody will be like, what if we don't want to modify the matrix in place? What if we don't want to make any changes to a matrix? You can use a set, right? It's very simple to use a set. So what I mean by a set is you can have a set data structure, right? And each time you see, so wherever you see the matrix, wherever you see this addition we make, where you see this addition we make, right? This addition we make, instead of doing this addition, you just add it to your set. So that before you trigger, the call of spread right here, like here, inside the spread, just check if this guy is already in our, if it's already in our vested, right? If it's in a set, don't trigger it. Very simple stuff. But usually you're allowed to modify it in place. Okay. Does this make sense to everyone? Does this make sense? And it's a simple DFS. You can also use BFS. BFS can do this too. But I think the DFS is more intuitive. You can look at the BFS later. Can we go on to the next thing? Can we go on? Can we go on? Okay, good stuff. Okay, let's see the next thing. Now we're going to go into a certain pretty algorithm. It's so pretty, trust me. Okay, so you remember that we said that trees are graphs, right? But trees have to be connected, right? Trees have to be connected. So this is a tree, right? This is a tree. And a tree is also a graph, right? This is a tree is also a graph, right? But then the moment I add these, right, and I'm like this whole system, right? But this is not a tree. I mean, like this whole thing is not a tree. Why? Because it is disconnected. It's disconnected, right? But then this is also another one. So let's say this whole system, right? This whole system is not a tree, but it is a graph, right? Then the question can be, find the number of connected components, right? Find the number of connected components. So here, let's number these 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So here there are 3 connected components, right? We have, we have this whole thing forming one connected component, this whole thing forming another connected component, and this one forming another connected component, right? So we have 3 connected components here. The question is, how do we find this? And as I told you, there's no graph question. I'm going to give you a graph like this, right? So the input to this question will be something like, let's clean this to get more space. So the input to this is going to be something like, node 1 to 2, right? There's an edge from node 1 to 2. You're going to get the edges, right? So 1 to 2 is an edge. Then 2 to 4 is an edge. That's how it's going to be. Then, 2 to 3 is also an edge. Then 4 to 5 is also an edge. So it gets the input like this. 4 to 5 is an edge. Then 5 to 6 is also an edge. Then 7 to 8 is an edge. Then 8 to 9, we've discussed this already, that you're going to get the input something like this, right? And then we're going to be like, maybe 10 to itself, no idea. I guess we can just put 10 here. Maybe let's make 10 is an edge to itself, I guess. I think that's fine, right? Then we do something like this, right? You're like, okay, so I mean, for now we can even ignore the 10. I mean, we can still add the 10, but like, I think to make cleaner if we do not. Okay, so then we have one that I'm finding number of connected. So this is the input, right? So this is our input. So you can just call it edges, right? Edges, right? They won't find the number of connected components. Now, welcome to the algorithm. Please, an algorithm. Follow me carefully. See, that's the reason why sometimes we're like, when you're practicing, right? Like, you've now started, right, on a certain topic. Don't spend like 1 hour trying to come up with things. Like, you're not going to, like, it's not going to work. See, this an algorithm people like spend years or months or something to come up with. If I give you like maybe days, like, or even the whole decade, you probably will not come up with it, right? Because you have other stuff to do with your life, right? So just learn them, right? And apply them in many ways. Okay, now let's go on. see how we're going to do it. I have a way of, of doing this thing. So I'm just going, I think it's very intuitive to understand it. So let's do something here. I want to create two things, right? First of all, what I'm going to tell you is that the nodes are labeled from, let me do something. I want to add another one. I want to make it simpler for people to make it make sense. Let's add another node here. And let's just call it node 0 because of what I'm coming to show you. Okay, so node 0. So what I'm going to tell you is that we're going to have two lists, right? We're going to have the rank list, and the parent list. The rank list and the parent list. Follow me carefully. Now, the parents list, please follow me carefully. The parents list, right? Now, as you can see, the nodes, are labeled from 0 to n, right? So here is from 0 to 9, right? For this input, 0 to 9. Almost always they give you a question like in this one, so they can easily manipulate, right? Like the range is bound, right? Okay, so I also have to use a dictionary, but I want to use a list. So the parents list, right, is going to be the parent of a particular node, right? The parent of a particular node. Now, at the start, right, we don't know what is connected and what is not connected. So we're going to let every single node be a parent to itself. Please follow me carefully. So this means that, right, this means that 0 is going to be a parent to itself, 1 a parent to itself, 2 a parent to itself, 3 a parent to itself, 4, 5, 6, 7, 8, and 9. Every node is going to be a parent to itself, right, at the start, because we don't know who is connected and who is not, right? So let's make this assumption. Then rank. Now, rank is simply going to be, right? Now, listen carefully. So rank, if I have two nodes like this, right? Assume I have two nodes like this, node 1 and node 2, right? The rank of node 1, right, is simply going to be how many nodes are looking up to you. What do I mean? We're going to choose one of them as, as a king or as a top down or whatever you want to call it, right? So here, assuming I want to make this guy the king, I'm going to be like the rank of 1 is 2, the rank of 2 is 1. So rank is more like who is on top of you. Rank is more like who are we all looking up to, right? If it becomes a tie, just to choose any of them and it's going to work, right? So rank is like, whom are we looking up to? Who is the champion amongst us, right? So 1 and 2, they both be like, so if they, so here they have the same rank, right? Here they have the same rank, right? Before you join them, they all have the same rank, 1-on-1. Everybody's looking up to itself, right? We're like, now I want to join you, right? If you want to join them and they have the same rank, you choose any of them. If you want to join them and one is bigger, right? Let's look up to the bigger one. Does this make sense? What rank means? So at the start, everyone has a rank of 1. Everyone is looking up to itself. But if it happens they have to join some two nodes because they're connected by an edge, right? And they both have the same rank, you can choose any of them. Else, just choose the bigger one, right? To be the king and increase its rank. So assume that you come and like node 1 already has a rank of 2, and this guy has a rank of 1, right? Then just increase the rank of, this one, right? This one will surrender, will give all its subjects to this guy. So it becomes 3, this guy still becomes 1, right? Assuming when you came to join them, this guy had a rank of 5, and this guy had a rank of 2, right? The 5 becomes the champion, right? 2 go and look up to 5. Then this becomes 7. Just add the rank of this guy to this guy. This guy still maintains his rank at 2. Does this make sense? What rank is? Does it make sense? Before we proceed, this is what rank is. So we discuss parents. This is rank. Does rank make sense? It can be like repeat or something. But I just want to make sure everyone gets it. Does rank make sense? Does it? Does it not? Does it not make sense? Too much silence. Hello. Yeah. Okay, let me repeat. Okay, so rank. What is rank? So rank is rank, right? The normal English rank, right? Then we say we're going to consider a few conditions. 1, assume you are joining 2 nodes, right? So at the start, so define rank as who are you looking up to, right? Who are you looking up to? So at the start, right, every node is looking up to itself. So as you can see in parent, at the start, we're like every node is a parent to itself. Then for rank, we're like at the start, everybody's looking up to itself. But now I have to join you, right? I have to join you 2 nodes together. Why? Because there's an edge between you, right? There's an edge between you. So I'm going to join you together. So when I join you together, I'm going to have to update your ranks, right? How am I going to update the rank, right? Okay, so I'm going to update the rank. If you have the same ranks, right? If you have the same, let's assume you have 1 and 1. And the value of your rank simply means how many nodes are looking up to you, right? So if there are 2 nodes looking up to 1 and 2 nodes looking up to 2, right? If they're the same, right? You can choose any of them as a champion, right? So let's assume I choose 1 as a champion. I'm like, hey, everybody should look up to 1. Then that means that I'll just increase, or I'll just increase the rank of 2 by the same rank. I'll increase the rank of 1 by 2, and that 2 is from here. So I get 2 plus 2. That means that all the nodes looking up to, these 2, right, should now also look up to this guy, right? So now the total rank for this guy becomes 4, right? Becomes 4. Then I'll maintain the rank of this guy. In the other way, assume that node 1 had a rank of 5 and node 2 had a rank of, let's say, 3, right? Then for now, it's clear that 1 should win because 1 already has too many people looking up to him. So let's give him more job to do, right? So I increase the rank of, this guy to be 8, right? That means that even the 3 people looking up to this guy too should also come and look up to 1, right? Does this make sense? The 2 conditions. If they're the same, just choose any of them and then increase that one you have chosen by, the rank of the other one. If they are different, choose, the one who has the greater one and increase its rank by, that of the smaller one. Does this make sense? Does this make sense? Okay, good stuff. Okay, so let's then move from here, right? And so this is what rank means, right? So that is simply what rank means. So at the start, what we are going to simply do is we're going to give every single one a rank of 1, right? Because at the start, everybody's looking up to their own self, right? Everybody's looking up to themselves. So there are 9 things, right? 9 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Everybody's looking up to itself. Now here comes the cool stuff. So this is initialized. These are the only 2 things you need to initialize. Now let's come here to our graph, right? So this is our input, right? This is our input. So see how we're going to do this. Now we're going to take every edge. So this is an edge. We take every edge, right? We take every edge. Then we try to join them together, right? And in joining them, we call the word union, right? Let's call it a def union. And union simply takes 2 nodes. Let's call them U and V. Let's just call them A and B. A and B, right? And then we try to join them together, right? They're simply coming to join them together, right? So here, if I take, node 1 and 2, right? Node 1 and 2, I think we added 0. Let's just add the 1. Let's just go ahead. Node 1 and 2, so that's like this node, these 2 nodes, right? We want to join them together, right? We just want to join 1 and 2 together, right? So that's what we call union. Now let's see how we union them, right? Let's see how we union them. To join 2 nodes, right? In this algorithm, what you do, right? So let's just write here. You want to join 1 and 2 together like this. You do 2 things. 1, you find their parents. You find their parents, right? You're going to find the parent of 1 and you're going to find the parent of 2, right? So let's just write it here. So let's call the parent of 1, right? The parent of A, we can just call it PA. PA, let's call it find, right? Find the parent of A. Then you find the parent of B. Assume you have this find function. Assume it's working, right? Assume you have this find function that finds the parents for you. Then parent of B, we also call find on B, right? So we've got the parents of A and the parents of B, PA and PB, right? This is what you do. So to join 2 nodes in this algorithm, first find their parents. Then the next thing you do, right? Then you compare the ranks of their parents, because that is what you care about, right? So that's when rank comes in. Then you check if the rank of A, right? So how can we get the rank of the parents of A, right? We have the rank list here, the rank, array you have here. This is the rank list you have here. So you can simply be like, if the rank of, what do you call it? Of, what's the guy again? Parents A, right? Is greater than the rank of parents B, right? Now we know what we do in this case, right? We know what we do when we get to something like this. The rank of parents A is going to the rank of parent B. Everybody goes to look up, everybody looks up to, what do you call it? Up to that guy, up to, what do you call it? Up to A, right? So it becomes rank of parents A should now be increased, right? Plus equals rank of parents B, right? Else, I'll add another line here. So that's why I'm just moving this down. Else, the rank of parent B is increased by the rank of parent A. See, it's an algorithm. That's why, if something is not familiar to you, just embrace it, just learn it, right? Like it's a new thing you're encountering. If it's something you already knew, we wouldn't be here talking about it, right? So if you get to a point and it's new to you, just embrace it, right? Like that's how the learning process happens. And the girls will tell you, like, confusion is so cool, right? Especially when you get to the part where you're beginning to get enlightened, right? So we've discussed this algorithm already. So assuming 1 and 2 are their parents, right? Because at the start, everyone is a parent to itself, right? Then we come here like, okay, is the rank of parents A here, the rank of 1 is still 1 itself. Is it greater than that of 2? Then give all the remaining jobs to this guy, right? Give all the remaining jobs to this guy, to 1. right? Else, what do? Else give it to 2 and so on and so forth. The next thing you do is you update their parents, right? This is how you update the parents. That the parents, right? The parents of, of PB, right, should not be the parents, right? Of the parents of B should not be the parents of A, right? And then we do the same thing here. The parents of A should simply be equal to the parents of B. And trust me, we're done with the whole union algorithm. And this is the whole code for union. This is the whole code. You just have to write the code for find. That's even way simpler than you can think of. Please take your time and look at this code before you proceed. Take your time, look at this. Let me know if something does not make sense. Take your time and just look at this. Ask any questions you have. Is someone asking a question?
I'm just saying you mistype like parent to ranks in the if section.
Yeah, in the if section. Here.
Yeah, I'm saying like the next line. The parent of B is equal to the rank of.
Oh, it's supposed to be parents.
It's
Thank
supposed
you.
to be like parents.
Yeah, it's supposed to be parents. Thanks. So this is supposed to be parents. So that's like the champion one wins, right? Like if I'm joining two of you like this, right? And your rank is bigger than me, then I now begin to worship you. Right? My parents have to worship you, right? We all have to worship you. Because I'm already worshiping my parents, right? And I'm bigger than my parents, then my parents should worship you. So something like this. If I answer to this guy, right? And you come and you're bigger than this guy, then this guy should not answer to you. So by implication, I'm also answering to you, right? So that's basically, the union algorithm. Like what we're actually discussing is called the union find algorithm, right? I just also call it the disjoint set algorithm, right? I just also call it the disjoint set data structure. We call the union find. So as you can see, we've already seen union. That is the union code, the whole union code. Then we go to find, and find is the last function we're going to implement. Then we are done. The last one is what we call find. I don't think we can do shortest path algorithm. We want to just do minimum spanning trees to do too. I don't think it's possible. So let's see find. Find, as we can see, let's say find takes a node. Let's just.
I have a question.
Yeah, what's the question?
You said?
Oh, with the last implementation.
Yeah, so the ranks and the parents, are they like specified, or you're supposed to do that yourself when you're
yeah, you're supposed to do it yourself. So the only thing you get as input to the question is this guy. I mean, they will tell you that the nodes are numbered from 0 to n, right? So then they give you the edges, right? So this is something you specify yourself, right? That, okay, so every index, right? Every index represents a node, right? It represents a node. So index 0 represents node 0. Index 1 represents node 1, right? So at the start, every node is a parent to itself. So node 0 is its own parent, 0. Node 1, the parent is 1. Node 2, the parent is 2, right? So every node is a parent to itself. Then rank is how many nodes answer to you, right? How many nodes answer to you? At the start, every node answers to itself, right? Because you don't know who's joined to who, right? Then you just use a for loop to go through your set of edges, right? So you take this first edge, then you're like, now, this, an edge is simply 2 nodes, right? An edge simply means 2 nodes, right? So when I say an edge, I mean node 1 and node 2, right? And that is from the input, right? You're like, okay, take these 2 nodes and join them together, right? And union them together. So how do I union 1 and 2? Well, I find the parent of 1, I find the parent of 2, right? If one's parent has a higher rank, right, then let two's parents answer to one's parents, right? And that is how it's answering to it. How does two's parents answer to one's parents? Let two's parents be one's parents, and increase the rank of one's parents by the rank of two's parents. Else you do the other way around. Does that make sense? Find it's a bit tricky, right? But it's so pretty, trust me. Such a pretty algorithm. We will visualize it actually. But I want you to get like the algorithm down. Does this make sense? Can we go to find? Find is simply finding the parents. That's what find does. And let's see how we can find the parents. That is when this guy is coming to do very cool stuff. There's actually an algorithm called path compression, which I may or may not mention it right now. We may probably be doing next week, so people don't get. But it's you can solve it without path compression actually. Okay, so that's what we can do here. So let's say we can find the parent. We want to find the parents. We can be like, okay, let's find the current parents. The current parents, how can I get your current parents? It's simply parents of A, right? Like if I want to find your parents, all I need to come and do, look at something carefully. If I want to find your parents, all I have to do is to come and look inside the parents one and be like, so assume A is 4, can just come and look at the index 4. And I'm like, okay, you are there, right? But then it's possible, because of this thing you're doing, you can see that we're actually updating stuff. So you get to some point where, this guy, right? Like that's not like really the case, right? It's going to get to some point like that thing we drew, right? Let me show you here. So we are like this node 2 is answering to, let's say, node 4, right? Let's say node 4 has a parent that is node 5. And then we bring some new node here, right? Let's say node 6. Then, then we get to this part here. Then we find out that node 6 rank is bigger, right? So what do? We are like node 5 answer to this guy, right? So what the find algorithm is going to do is that it's going to, so let's assume we want to join 2 to some other node, right? I don't want to join 2 to some new node, right? As you want to join 2 to, let's say, node 1, right? Only join these 2 things together. That's what you want to do now. Please follow me carefully. It's actually very simple, right? As you want to create this edge, you want to create this edge, the green one I've made here. But then before you want to create this edge, you realize that 2 answers to 4 and 4 answers to 5, right? And 4 answers to 5. Let's do this. So 2 answers to 4 and 4 answers to 5, right? And 1 also answers to 6. But now you want to marry 1 and 2, right? You want to join them together, right? That is what I want you to do. So assume that in this algorithm, the inputs, right? Assume that the input you have to this question is 1 and 2. You want to union 1 and 2, right? Union. You want to union 1 and 2. So you want to find the parents, you want to find the parent of 1, right? You want to find the parent of 2, right? But let's see how we can find the parent of 1. To find the parent of 1, right? We simply call the find algorithm, right? And then, we can simply check it and see, right? You can simply check parent of 1, then that is going to give us 6, right? But let's look at the parent of 2. To find the parent of 2, you find the parent of 2, that is 4, but you don't stop there, right? You find the parent of 4 also, that is 5, right? Please follow me carefully. Follow me carefully. It's not hard. It's not bad. Let me go over it again. Look, let me cut this thing. Like, it's actually not bad. Just follow me carefully. Let me cut this guy and bring this guy down. I think that'll make. Look here. Look at what you're trying to do here. Let me move this one here. Just take a look again. So you have these 2 components, right? You have these 2 things, right? And now what you want to do is you want to union 1 and 2, right? Look at this carefully. You want to union 1 and 2. Okay. So now you know that 6 is a parent to itself, right? So let me just do that here. 6 is a parent to itself, and 5 is also a parent to itself, right? So far, right? So 1 is a parent to 6, and 6, 6 answers to itself, right? Here 2 is a parent to 4, but 4 does not answer to itself. 4 answers to 5, and 5 is, an order on its own, right? So this is how the find algorithm works, right? So now you call, you want to union 1 and 2. So you call find A on 1, right? So A is 1. So you come to 1. So what do we do? So at 1, you're going to look into the parents list and be like, who is the parent of 1? That is 6. Then you ask yourself, who is the parent of 6? And that is 6 itself. Then you have found the parents, right? So it's kind of like a bubbling up thing, right? You go up. So you come here, you're like 2. Who is the parent of 2? 4. You're like, who is the parent of 4? 5. Who is the parent of 5? 5 itself, then you end. So that's the whole code for the find algorithm. It's like you're going up, you're going up the hierarchy, right? You're going up the hierarchy. So if I write this in code, it is simply while parents is not equal to the parents of parents. Look at this. Then what do? You just set parents to be equal to parents of parents. This has no path compression, nothing. And then you can simply return parents. Look at this code. Let's analyze this code here. Let's just make this P. So so P is equal to this. Let me write as P while parents of P is not equal to P. Then P is equal to the parents of P, right? Then here we can return P. So let's look at this algorithm. So this lengthy thing I just discussed here, finding this thing, this is simply the code. So let's see what the code is. Let's go through the code. So I want to find, the parent of 1, right? I want to find the parent of 1, right? So I first go into my, my parents list, right? Then I find out that the parent of 1 is 6, right? So at the start, we are like the parent of 1, we are like P is 6, right? P is 6. How do I find P of 6? I just went to the parents list, then I indexed 1, right? Then I'm like, okay, it's 6, right? Parent of 1 is 6, and it's obvious from my diagram. Then I'll go to the loop, right? Then I'm like, well, the parents of 6 is not equal to 6, but as you check, the parent of 6 is indeed equal to 6. So this loop will not execute. Then I can return 6. Does this execution make sense for this guy? Please take a look at this again. How I'm calling this find function, right, on this setup here. Then I return 6. Please go through and make sure it makes sense to you before I continue. We're actually done with the code. Last thing just write it might follow, but then we are done. We're basically done with the code. Then we just increase some counter and we are done. But this is how we implement find and union. Does this make sense? Calling it on this first component here. Now let's look at this guy here. Look at the second one. So I'm like, okay, find the parent of 2, right? So I find the parent of 2, and the parent of 2, right, is 4. So I'll be like 4. Okay. Now, while the parent of P, right? Now look, P is 4. While the parent of P, that is 4, is not equal, to P. So the parent of 4 is 5, and 5 is not equal to 4, right? They're different, right? Then enter the while loop. When I enter the while loop, what do? I update P, right, to be its parent, right? So instead of P being 4, here update P to be its parent, that is 5. Then the loop will come again, right? So then the loop will come again. While the parent of P is now 5. While the parent of 5 is 5, it's not equal to 5. Well, 5 is equal to 5, so the loop ends. I end up returning 5. So when I call, so here, after I return from the find, code, these two guys are going to have their parents 6 and then 5. And then we can simply, do the join in here, right? We can do the union in here, and then we are done. Does this make sense? Does this make sense? I'll actually show you the code, and I'll show you the code with. Does the algorithm make sense a bit at least? How to union two things. You find their parents, and then you do this. We can actually optimize this code here using something called path compression, but I don't need it like right now. We can do it next week. And then we come here. But that's simply the union find algorithm. And so let's solve the question. So to solve the question, once you have these two functions, all you need to do is to simply do this. Right? So your input to the question was edges, right? Were these edges. This was the input, these edges. So what you simply do is that for every edge, so every edge that is A and B in edges, right? What I will simply do is, well, I'll try to, union, right? I'll try to union A and B, right? I'll try to union A and B, right? But let's look at a slight modification here. I want to union A and B, right? But then look at this carefully. You know that assuming, right? Assume this is what you have, right? Assume this is what you have. Let's follow me carefully. Assume this is what you have. I know. Graphs is lots of very cool stuff. I know. I'm also obsessed with it too. Right? Assuming now you want to union 3 and 4, right? You want to union 3 and 4. Can somebody tell me what I'll get if I find the parent of 3 and the parent of 4? All I get. When I find the parent of 3 and the parent of 4, all I get. Assume this is the state of one component now, right? Like you've called union, multiple times. And you have something like this, where this guy is like, where the rank of this guy is 3, the rank of this guy is 2, rank of this guy is the rank of this guy is 1. And now I want to union 3 and 4. So assuming the input to your union is 3 and 4, what will I get as a parent? Because here I call parents, right? I call parents on 3 and I call parents on 4. What will I get as a parent? What will I get as a parent? We are almost there. We're actually almost done. I kid you not. What will I get for the parents of 3
Is
and
it
4? Will it be 2? Look at the path compression algorithm. The moment you see 2, right? 2 will try to climb up, right? So here 3 will get to 2, but 2 will climb up to 1, right?
Okay.
4 get to 2.
1.
Exactly. So it's 1. So they're both going to get 1, right? And so you see their parents are the same. Each of the parents are the same. That tells you they are already part of a component. Can you see they're already part? That means they're already joined together, right? That means they're already joined together, right? So inside the union code, you can simply do if the parent of A is equal to the parent of B, right? You can simply return maybe something, you can simply return false. That means you didn't join them, right? But if they have different parents, that means they have to be joined, right? That means they simply have to be joined. So here we can return true, right? They can return true. Does this make sense? So I return false if I didn't have to join you, means you're already joined, right? You're already joined together. Does this make sense? Does this slight modification make sense? Right? If you have the same parents, I'm like, I didn't join you, so false. But you had different parents, I'm like, okay, I joined you. Right? Then I can return true. Does this make sense? Let me check the chat. Yeah, good stuff. Good stuff. Okay. So now the question is, okay, want to find how many connected components are there, right? How many connected components are there? So let's look at it carefully here. I just want you to see it for yourself. So let's look at it here. We're actually almost done. I think we've really used a lot of brain cells today. I'm actually close early. Okay. So let's look at this thing here, right? Let's look at this guy here. So wait, are people tired? Like, is it becoming a lot? Is it becoming a lot? Anyone? Is it becoming a lot? Is it becoming a lot? Is it becoming a lot? Oh, I want some response. Like, we have one last thing we're done actually. Is it becoming a lot? No response. Okay, that means we're actually done. We're actually almost done. One last thing. So look at
Cornelius?
uh-huh.
I'm just curious. Like after you're done, could you like conduct a poll to see ask how many people have either heard of Union Find or even know how it works, like not implementation, but like how it works.
Yeah, how the algorithm is.
Diagram or something.
Yeah.
Yeah. Or even heard of it.
Mm-hmm. Yeah. So let's look at something here. So look at this structure we have here, right? At the start, we made a lot of bold assumptions, right? We are like, everybody's a parent to itself, right? Everybody is its own master, right? So we can say that, okay, then the number of components is n, right? It's simply n, right? So did I say n? It's like n plus one, right? Like anyhow you want to think about it, right? That's like every node, is a component on its own, right? We're like every node is a component on its own. Every node is a component on its own. But the moment we join any two, we have decreased the number of components by one, right? Listen to me carefully. At the start, we are like, let's assume, right? At the start, we're like, there's no edge between them. That's what we just did here, right? We're like, assume everybody is like on its own, right? Then, we take like, 1 and 2, then we join them together. We take like 2 and 4, then we join them together, right? So at the start, we're assuming that there are, let's say, 10 nodes, right? We assume there are 10 components. Then once I join 1 and 2, I have decreased the number of components to 9. Why? Because now these guys count as 1, right? Then again, the moment I join, let's say 2 and 4, so I move to 9. And when I join 2 and 4 too, I've moved it to 8, right? Because I'm like, these, 3 nodes are not independent, rather, they count as one person, right? So I'll decrease it again. Then the moment, I join 2 and 3 also here, 2 and 3 here, I'm like, oh, actually there are 7 components, right? Then the moment I join 4 and 5, right, I'm like, okay, oops, they're actually 6 components, right? So I'm just decreasing the number by that, right? So that is simply the algorithm. We are done, right? So we're like, at the start, let our results be, let's say, n or n plus 1 or whatever it is, right? Here, technically it's actually n plus 1, like there are 10 nodes because we start from 0 to n. Like we start from, let's assume the question tells you what n is, right? N is 10, right? So each time you do, and you see that each time you're able to successfully join something, how do you return true, right? So if union, right? If I join anything, just decrease n by 1, right? Decrease n by 1, and at the end, just return n, right? So if you look at this simulation right now, if I do 4 and 5, I join them. If I do 5 and 6, I join them. I decrease this guy to 5. If I do 7 and 8, I decrease this guy to 4, right? Then if I do 8 and 9, I decrease this guy to 3, right? And then, there's a 0 and 1 here that we can add, right? There's a 0 and 1 and 1 we didn't add. So there's a 0 and 1. If I join 0 and 1, 2, I decrease this guy to 2. And now I'm done, right? And you can see there are 2 components here. There's 1, then there's 2, and then we are done. Very cool stuff. I know, I'm impressed too. It's a very beautiful algorithm. God bless those people who did it. And this is the same algorithm we used to implement Kruskal's algorithm in the minimum spanning tree. We do go on next week. Very, very cool stuff. Okay, before I do what Julian said, I'm going to show you a couple of questions that use this algorithm. There's actually a bunch of graph questions you can actually optimize, exploit this algorithm for, and it is really cool. Anyone confused? We're actually done. Like, this is the whole question. We're actually done. This part is just some extra step. But if you know how to implement these two, like, you're done. And it's not really that hard, right? Just find the parents, right? Union. Just find their parents, assume, and how African code today is how you write in an interview mostly, right? You've not implemented find, but just write it as if it's already written for you. Like, just be like, so I find the parents of A and I'll call find A, right? Then after they come and even bother about find. Because sometimes you don't have time to complete, your code. So you assume the function is, then just write the function name, say, just be like, okay, so this is going to find the parents of A. If you get time, you're not even able to implement A, the interviewer knows what you're saying, right? They know your logic, right? So don't go and implement find A first before you put it in. No, start from top to down if you can. Just write the name of that function, right? Then, finish it as if it were like, okay, so now let's implement find A, right? That is how it's done. Does it make sense? Does it make sense? Does this make sense? Okay, Julian, I'm giving you what do you call it? The thing so that you can create the poll. So let me know when you're done as I try to.
I have a question.
Yeah.
Can you? Yeah, so like everything sounds great, but I just want you to clarify something for me.
Mm-hmm.
So like when you are creating the parents, But I noticed like you were doing like the parent starts from 0 to 9, right? So like, does that mean the parent is all the distance?
The node itself.
Literally all the nodes in the graph, the tree, right?
Yeah.
And in case like, let's say in case like there is no 3, in case there's no 3, so in case there's no 3, does that mean the parent will not have like a 3 in it, right?
Oh, so as I said, when they give you the question like this, to make it easy for you, they tell you the nodes are numbered from 0 to say n or n minus 1, right? So we're going to get node 0, node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8, node 9, node 10, right? So what we are basically doing here is that we are like node 0, right? Node 0. So this node 0, index 0, node 1, node 2, node 3, right? So the parents of node 1, so like the index is the same as the node, right? That's what why you should think about it. Like the index is the same as the node, right? So assume that I join, look here, assume I join 1 to 2, right? I join 1 to 2, right? Then I made 2 the champion. Then I'll come here and then I'll update. Let's do it quickly. I'll come and I'll update 2's parent to 1 now. That's what I'll come and do, right? Then I increase the rank of 1 to 2 like this. Does it make sense? Does this make sense?
Yeah, so, it does.
Yeah. So the indices are like the nodes itself. Anytime you do a join, you kind of like manipulate it, right? Every time you union them, you update. So here I joined 1 and 2, right? And I made 1, the champion. So I'll change the parent of 2 to no more be itself, but to be 1. And I'm going to increase the rank of 1, right? By, the rank of 2, by the original rank of 2, which was 1. So 1 plus 1 becomes 2, right? So that's what's happening. And we are actually, I just want to show you, I just want to show you, what do you call it? A question like on LeetCode and stuff. We will add it to this week's problems and then we are done. We're actually done. Okay, good stuff. Please watch the recording again if you have to. I came across this algorithm. I've actually learned it like a year ago or something. I had people talk about it and make noise with it, but yeah. Okay, let's see. Let me just show you something. Then we are done. Good stuff. Oh, I'm not sharing my screen. Okay, can you see my screen? Can everyone see my screen? Okay, good stuff. Please do want to go through these problems if you haven't, like trying graphs 1, the two. Last week we just gave 4 questions. And even some of the questions actually repeated from graphs 1. It was intentional. Please do it because some of you are doing personal practice and everything. I don't want you to be burdened, right? So we're just trying to balance everything together. So please do well too. Number of connected components. Oh, this is actually a LeetCode premium question. But don't worry, I've still got you. See, so there's a whole subsection on its own. It tells you a lot of cool stuff. You can even use to solve a number of islands. Let's see number of islands. Oh, this is the question we solved at first, right? Like, you don't need to count groups of ones, right? So, this, like this, then it comes down, like this is a whole group of ones. This is literally the question we solved. If you go to like solutions by people, right? Like everything we're doing is so crucial, right? So basically this is the grade. Oh, you see, these people are the people who write code I don't like. They've placed the thing into 4 times, right? Like I'll just use a for loop, right? So like if it is 1, then they recall the spread, then they call spread on it, right? Then that's basically what they do. And you see, they instead of them setting it to 0, they don't set it to 0, right? They set it to pound, right? They set it to pound, but I set it to 0. But see, the same thing, right? Same logic, right? And before you process it, just flip it to 0 so that when it comes in, it's going to, so here it says if it's not equal to 1, don't call it, right? So you see the same thing. That's a question we actually did. And many graph questions actually exploit this, right? Like, especially the matrix ones. It's just like, call the thing for all time. I don't write code like that guy. Please use a for loop like me. Thank you. Because why not? So let's see surrounding regions. Like many of the questions you come up with actually adapt to the same thing. What are surrounding regions? So give me my capture all regions that are 4 dimensional surrounded by an X. Oh, this actually sounds like an interesting question. We can look at God next week. So you want to, so if this guy, so this guy here, what is it again? Okay, so if I take this guy here, I think it's also a more connected components thing. If I take this guy here, it's surrounded by an X here, it's surrounded by an X here, so it's surrounded by an X here and an X here, like this whole region. So you just want to capture this whole region. I think one way you can actually do this question is there's no way any guy at the bottom, at the border can be surrounded. Look at this. This is actually also a reverse thing. Look at this. Don't worry. I said up, we have to leave. Let me just go and show you the union find question. Then we're done. Redundant connection. I've been learning union find. I went to see this connect, solve this question from scratch. I was so excited when I did it. Right, this is also union find thing you can do. Right, let's look at it. Then we are done. We are done. Right. So let's say you have this. Right, union find. So you first union 1 and 2. Right. Right. So you find the parent of 1, find the parent of 2. Right. Then you union them. Right. So this is basically asking you if there's a redundant connection. So what that means is that like this guy, if there was no this edge, right, this thing would have been a tree, right? Like, but they add one extra edge and that causes a cycle, right? That causes a cycle. So they're like, we want to find that that cycle and delete it, and right, that's what they want to ask for. In other words, it can even use to find whether there's a cycle, right? So that's what they're asking for. So like, if they remove this guy, if they remove the edge 2, 3, right, there's no cycle, right? It becomes a perfect tree. So you can use union find for that. How can I use union find for this? Find the parent of 1, find the parent of 2, right? So now I want to union 1 and 2. So I find their parent. If they don't have the same parents, you can union them, right? But then if you find their parents and the parents are the same, that means you can't union them. And that's the edge causing the cycle. If you look carefully, right? So because assume these are joined already, right? Assume 3, 1, 2 are joined already. Assume there's no edge from 2 to 3, right? So assume 3 to 1 to 2 are joined already, right? Then now you begin to union 3 and 2. You find the parent of 3 is going to be 1. Find the parent of 2 is also going to be 1, right? Then the parents are the same. That means they're already joined together. That's another way to think of union find, right? That there's already a path to them, right? And then when that happens, you'll be like, oops, I'm sorry, you are the culprit. So if you look here, let's look at the solution. You can use DFS, which doesn't seem pretty. You can see union find, so pretty, right? Like so pretty. You see the similar thing we did. They even use rank and parent, they copied us, right? Lots of cool stuff. So yeah, and that's it for today. We will actually upload the questions so you can actually practice on. If you, what do you call it?